You ever just stand under a huge bridge and look up? Or, watch one of those giant construction cranes lifting something massive?
Oh yeah, it's pretty awe-inspiring stuff.
It really is. And when you think about it, all these structures, from like basic roof supports to really complex machines, they all work because of these basic rules, these principles of force and balance.
Absolutely. It looks static, right? Like
Huh.
it's just sitting there. But inside, there's this whole invisible dance of forces going on, all carefully calculated, perfectly balanced, figuring how they stand up. That's structural analysis.
And that is exactly what we're getting into today. This is our deep dive, our
Mm.
mission to get you quickly up to speed on how engineers figure out all those forces in things like trusses, frames, machines.
Yeah, and hopefully reveal some, pretty surprising insights into how clever the designs really are. Often quite elegant, actually.
So, what can you expect?
Well, we'll start with the basics, the sort of building blocks.
Hmm.
Then the key assumptions engineers make shortcuts, almost, to simplify things. And then we'll hit the big methods,
Mm-hmm.
the method of joints and the method of sections. Powerful tools. We'll even peek at how this works in 3D and for more complex stuff like cranes or even just a pair of pliers.
Sounds great. So, thinking about that scale, where do engineers even start? How do they build up these massive structures? It begins with trusses, right?
That's right. Trusses are fundamental.
So, what is a truss exactly?
Okay, think of it as a structure made of slender members,
Mm-hmm.
like street bars, wood, or metal. And they're only joined together right at their ends.
Okay.
The key is how they're arranged, usually in triangles. Triangles are inherently rigid, they don't easily deform,
Mm-hmm.
and most often you're dealing with planar trusses.
Meaning flat?
Exactly, they lie in a single flat plane. You see them everywhere, roofs, bridges,
Yeah.
they're super common.
Like the triangular supports in an attic, I always wondered how the actual roof load gets onto those triangle bits.
Yeah, good question. So for roofs, the weight isn't just spread out, it gets channeled through these smaller horizontal beams. Purlins, they're called.
Purlins, okay.
And those purlins transfer the load directly onto the connection points, the joints of the truss. And since the load is in the same plane as the truss, it becomes a nice, neat, two-dimensional problem to solve.
Hmm. Okay. And bridges, similar idea. Channeling the load.
Pretty much the same principle.
Hmm.
The load on the bridge deck, where cars drive, goes first to beams running along the road. Those are stringers.
Stringers.
Then stringers pass it to perpendicular floor beams. And finally, those floor beams dump the load onto the joints of the big side trusses that hold everything up. Again, all coplanar, all in the same flat plane.
Right. Now, speaking of bridges, sometimes you see on one end there's like a wheel or a curved metal plate it rests on, like a roller skate almost. What's that about?
Ah, yes. Those are rockers or rollers?
Yeah.
Super important, actually, especially for trusses spanning long distances.
Why is that?
Well, materials expand when they get hot, contract when they get cold, right? And loads shift like a heavy truck moving across. That roller or rocker allows the whole truss structure to just move a tiny bit, expand or contract freely.
Ah, so it doesn't build up stress.
Exactly. Without that freedom, you'd get huge internal stresses building up just from temperature changes or load shifts. It's a really smart way to avoid potential problems. Very clever design.
That makes sense. Okay, so when we're analyzing these, trying to find the forces inside the members, there must be some ground rules, some simplifications engineers make.
Oh, absolutely. These assumptions are crucial. Otherwise, the math gets incredibly complicated very fast. So assumption number one, and it's a big one, all loads are applied only at the joints.
Only at the connection points.
Right. And for most bridges and roofs, that's pretty accurate because like we said, the purlins and floor beams do bring the load right to the joints. We also usually neglect the weight of the truss members themselves.
Why is that? Too small to matter.
Often, yeah. The loads they carry are way, way bigger than their own weight. If you do need to include member weight, you typically just split it half the weight acts on the joint at each end.
Okay, that's assumption one. What's the second?
Second assumption. The members are joined by smooth pins.
Smooth pins. Like frictionless.
Kind of. In reality, you've got connections made with gusset plates, those flat metal plates you see at joints, maybe bolted or welded, or sometimes big actual pins or bolts.
Right.
But we assume they act like smooth pins. As long as the center lines of all the members meeting at that joint line up perfectly, they're concurrent. Meet at one single point.
And why is that smooth pin idea so important?
Because those two assumptions, together, loads only at joints, and smooth pin connections lead to a really fundamental result.
Which is?
That every single member in the truss acts as a two-force member.
Two-force member. Okay, what does that mean practically?
It means the force acting on each end of that member has to be directed right along the axis of the member itself. It can only be pulling straight out or pushing straight in. That's it.
Ah, so no bending forces within the member itself.
Exactly. Just simple tension or compression.
Yeah.
It simplifies everything enormously. It's why you can build strong but lightweight things like bike frames or airplane wings.
Yeah.
You know exactly how each piece is working.
So just pulling or pushing. Let's quickly define those again.
Sure. Tension. That's a pulling force. Think T's for taut. It tends to stretch the member, elongate it, like pulling on a rope.
Okay.
And compression. That's a pushing force. C's for crush, maybe. It tends to shorten the member, squeeze it, like pushing down on a column.
And knowing the difference is important for design.
Oh, absolutely vital.
Yeah.
Because members under compression behave differently. They can buckle, sort of bend sideways if they're too thin, even if the material itself is strong enough. It's called a column effect. So compression members often need to be thicker or shaped differently than tension members carrying the same amount of force.
Got it. Tension pulls, compression pushes, and compression members might need to be beefier to avoid buckling. And how do you actually build these trusses? You start small.
You start with the most basic rigid shape, which is a triangle, just three members pinned at the corners. That's stable. Then, to make a bigger truss, what we call a simple truss, you just expand on that. You add two new members and connect them at a new joint, forming another triangle attached to the first.
Yeah.
You just keep adding pairs of members and joints. It's very modular, ensures the whole thing stays rigid.
Okay, foundations laid. We know what a truss is, the assumptions, two force members. Now the big question, how do we actually find those tension and compression forces? Method 1, the method of joints.
Right. This one's based on a really elegant idea. If the whole truss is stable, in equilibrium.
Meaning not moving or accelerating.
Exactly. Then every single joint within that truss must also be in equilibrium. All the forces acting on that tiny pin connection have to balance out perfectly.
So you zoom in on each connection point.
Precisely. You isolate each joint one by one and draw its free body diagram, a little sketch showing just the joint and all the forces acting on it. For planar trusses, the flat ones, all the forces at a joint meet at a point and lie in the same plane. So you only need two equilibrium equations to ensure balance. Sum of forces in the x direction equals 0, and sum of forces in the a direction equals 0.
So horizontal forces balance, vertical forces balance.
That's it. Left equals right, up equals down for every single joint.
Now, when you draw that diagram for a joint, how do you know if an unknown member force is pulling tension or pushing compression?
Good point. Sometimes you can just tell by looking. By inspection. You see the external loads, the geometry, and you can figure out, okay, that member must be pushing on the pin, it's in compression, or that one must be pulling, it's in tension.
But what if you're not sure?
When in doubt, the standard procedure is to always assume the unknown forces are in tension.
Yeah.
Assume they're pulling away from the joint in your diagram.
Or always assume tension.
Yep. Then you do the math, solve the equations. If the number you get for that force comes out positive, your assumption was right, it is tension.
And if it's negative?
A negative answer simply means your initial assumption was wrong. The force is actually compression, pushing towards the joint with the magnitude you calculated. The negative sign just flips the direction.
Oh, that's handy. So a minus sign doesn't mean you messed up, just that it's compression instead of tension. Okay, so what's the step-by-step process for this method?
Okay, first, start smart. Pick a joint where you know at least one force, maybe an external load or a support reaction.
Wait, sometimes you need the support reactions first, the forces holding the whole truss up.
Often, yes. You might need to analyze the whole truss as one rigid body first to find those reactions at the supports.
Okay, so find reactions if needed. Then pick a joint with one known and at most two unknown member forces. Why only two unknowns?
Because you only have two equations for each joint sum of forces in x, sum of forces in y. Can't solve for more than two unknowns with just two equations.
Makes sense. Then what?
Then, orient your axis. Set up your x and y directions on your free body diagram. Usually horizontal and vertical is easiest. Step 3. Apply the equations. Write out phi 0 and CVAR 0 for that joint, plugging in the known forces and the unknown ones. Remember, assume tension. Solve those two equations for your two unknowns.
And you get the magnitude, and the sign tells you tension or compression.
Exactly. Then, step 4, cascade. You take the forces you just calculated, making sure you use the correct sense tension or compression, and you use them as known forces when you move to analyze the next adjacent joint.
Ah, so each solved joint gives you info for the next one.
Right, it's like a chain reaction. You work your way through the truss joint by joint.
Let's try a quick example. Say a basic triangle truss, maybe holding up a sign. There's a 500 Newton force pushing straight down at the top peak joint. Where would you start?
Okay, perfect starting point is that top joint. Why? One known force, the 500N down, and usually just two members meeting there, so two unknowns.
Right. Draw the free body diagram.
Yep. You've got 500N pointing down. You've got the unknown forces from the two diagonal members meeting there. Assume they're both in tension, pulling away from the joint.
Oh.
Now, some forces in the E direction. Vertical. The vertical components of those two assumed tension forces have to balance the 500N pushing down. That'll give you one equation.
And then some forces in X.
Exactly. Some forces horizontally. The horizontal components of those two diagonal forces have to balance each other out. Second equation, solve those two.
Right.
You find one diagonal is actually, say, 707N in compression, pushing, and the other is also 707N compression.
Okay, so the negative signs told you they were compression.
Right. Now you know those forces. So you move to one of the bottom joints, that diagonal force you just found.
Yeah.
It's now a known source pushing into this new joint.
Oh. And that helps you find the forces in the bottom horizontal member and maybe the support reaction there.
You got it. You just keep stepping through, using what you learned at one joint to solve the next. It's very systematic.
Very cool. Now, sometimes when you're doing this, you find members that have zero force in them. What's the deal with zero force members?
Yeah, that happens. Zero force members are just what they sound like. Under a particular set of loads, they carry no force at all. No tension, no compression. Zero.
So why are they even there? Seems like wasted material if they're doing nothing.
But they are doing something important. They often add stability to the truss, especially like during construction before everything's fully loaded.
Okay, stability.
And they provide redundancy. If the loading changes, maybe wind load gets added or the main load shifts, those zero force members might suddenly need to carry a load. They provide alternative load paths.
So they're like structural backup singers or an insurance policy.
Yeah, structural insurance policy is a great way to think about it. You don't notice them until you need them.
Okay, that makes sense. Can you spot these easily without doing all the math?
Often, yes. There are two common cases you can spot by inspection.
Right, case one.
Case one, you have a joint where only two members meet, and they are not collinear, not in a straight line.
Yeah.
And crucially, there's no external load or support reaction applied right at that joint. If those conditions are met, both those members are zero force members.
Two members, not collinear, no load at the joint, both zero. Okay, case two.
Case two, you have a joint where three members meet. Two of those members are collinear, they form a straight line. The third member sticks out at an angle. Now, if there's no external force or support reaction acting at that joint that has a component along the direction of that third member, then that third member is a zero force member.
Okay, three members, two in a line. The third one is zero unless something is pushing or pulling it directly.
You got it.
Right.
Spotting these can save a ton of calculation time. You just identify them, mark them as zero, and they're effectively removed from your analysis for that specific loading.
Like in a Fink truss, that W-shaped roof truss, you can probably find a few zero force members in there just by looking at the joints using those rules.
Absolutely. Joints G and D in the typical Fink truss example are classic spots where you can immediately identify zero force members, simplifying the whole process.
Brilliant. Okay, method of joints is great for finding all the forces, but what if I only care about the force in, say, one specific member right in the middle of a huge truss? Is there a faster way than analyzing every single joint to get there?
Yes, there is.
Yeah.
It's exactly where the method of section shines. It's the strategic shortcut.
The strategic cut. Okay, tell me about it.
It's perfect when you only need forces in a few specific members, not the
Yes.
whole set.
And the principle, still equilibrium.
Still equilibrium. But instead of focusing on tiny joints, we say, if the entire truss is in equilibrium, then any chunk or segment of that truss must also be in equilibrium.
So you imagine cutting the truss.
Exactly. You pass an imaginary section line right through the members whose forces you want to find. This cut essentially slices the truss into two pieces.
And that exposes the internal forces.
Precisely. The internal tension or compression forces in the members you cut through now become external forces acting on the chunk of the truss you choose to analyze.
Ah, clever. And since you're looking at a whole chunk, not just a point, you have more equations.
You do. For a 2D segment, you have three independent equilibrium equations you can use. Sum of forces in x equals 0, sum of forces in y equals 0, and the sum of moments about any point on the segment must equal 0. Fex eps ua's, 5 boas.
3 equations. So that relates to how many members you can cut through.
That's the key.
Hmm.
Generally, your section cut should pass through no more than 3 members where the forces are unknown, because you only have 3 equations to solve for those unknowns.
The rule of 3. Got it.
What's the biggest advantage here? You mentioned moments.
The moment equation is the superpower of this method. It allows for really strategic problem solving.
How so?
You can often choose a point to some moments about where the lines of action of 2 of your 3 unknown forces intersect.
Ah, so those 2 forces create no moment about that point.
Yeah.
Exactly. They drop out of the moment equation entirely, leaving you with just one unknown, the third force. You can solve for it directly in one step. It's incredibly efficient.
Wow, that is strategic. Any other trick?
Well, sometimes 2 of the unknown forces might be parallel. In that case, you can sum forces in the direction perpendicular to those 2 parallel forces. Again, they drop out of that equation, letting you solve directly for the third unknown.
So it really lets you bypass a lot of steps compared to the method of joints if you only need a few specific forces.
Definitely. Think about finding a force in a diagonal member deep inside a truss. Method joints might mean analyzing joints A, then B, then G. Method of sections, you make one cut through that member, pick a smart moment point, boom, you've got your answer.
Okay, procedure then. Cut, draw, solve.
Pretty much.
Mm.
Decide which member forces you need. Make the cut through those members. Max 3 unknowns. Draw the free body diagram of one of the resulting segments. Usually pick the one with fewer external forces acting on it. Makes life easier. Assume tension for the unknown forces in the cut members, pulling away from the segment. A negative answer will mean compression, same as before.
Right.
Then apply the equilibrium equations. Strategically use min-mx, fis-x gonophones. Pick moment points wisely to isolate variables.
Let's take an example. Say a bridge truss, and we want the force in a specific top chord member, FBC, a diagonal FGC, and a bottom chord member, FGE. We make a vertical cut through them.
Okay, good cut. Section AA.
Mm-hmm.
First, you probably need the external reactions holding the bridge up. Find those first.
Right. Then we draw the FBD of, say, the left segment.
Good. Now, want FBC, the top chord. Where could you use some moments to make the other 2 unknowns disappear?
FGC and FGE both pass through joint G at the bottom, so some moments about G.
Perfect. Some moments about G, FGC, and FGE produce no moment. The only unknown left in the equation is FPC. Solve for it directly. Maybe it comes out positive tension.
Nice. Now for FGE, bottom chord.
Where do FBC and FGC intersect?
Looks like joint C at the top.
Right. Some moments about C, FBC, and FGC drop out. You solve directly for FGE. Maybe it's negative compression.
And the last one, the diagonal FGC.
Now that you know FBC and FGE, you could sum forces vertically. Almaty 0. The vertical component of FGC will balance out any external vertical loads in the vertical component of FBC if it's angled. Solve for FGC. Perhaps tension.
See? One cut, 3 equations strategically applied gets you all 3 forces directly. That's really efficient.
It's a very powerful technique for targeted analysis.
Okay, we've covered flat trusses really well, but the real world isn't always flat. What about 3D structures? Space trusses, and things with moving parts like frames and machines.
Right, let's move beyond the plane. Space trusses are just the 3D versions. Members join at ends, forming a stable 3D structure. Think transmission towers, roof domes.
And instead of the basic triangle, what's the fundamental 3D building block?
It's a tetrahedron. 4 joints connected by 6 members, like a pyramid with a triangular base. That's the simplest, stable 3D truss unit.
Do the same basic assumptions hold? Loads at joints, members are 2 force.
Yep. We still generally assume loads are applied only at the joints, and the connections act like smooth ball and socket joints, allowing rotation in all directions. And yes, members are treated as 2 force members.
So analysis, method of joints and sections still work?
They do, but things get a bit more complex.
How so?
Method of joints in 3D. Each joint now needs 3 equilibrium equations. Fis-x final, Fes-flingers. You're balancing forces in all 3 dimensions. This often requires using vector math, breaking forces into XYZ components. It can get pretty involved.
More bookkeeping. And method of sections in 3D.
Still works. You make an imaginary cut. But now, your cut segment has 6 equilibrium equations available. Sum of forces in XYZ must be 0, and sum of moments about the X, Y, and Z axis must also be 0.
6 equations. So you could potentially cut through up to 6 members with unknown forces.
Potentially, yes. Again, choosing the cut and the axis or moment point strategically is key to isolating the forces you want without solving huge systems of equations.
Okay, same logic, just more dimensions. Now, what about frames and machines? You said they're different from trusses?
They are. This is a really important distinction. Trusses, all two-force members. Frames and machines contain at least one multi-force member,
Multi-force
meaning a member that has forces acting on it at more than just 2 points,
Yeah.
or has forces that are not directed along its axis, or even has couple moments acting on it. Think of the main arm of a crane. It has the load, its own weight, forces at the pivot, force from the hydraulic cylinder. Lots going on.
So they're not just simple tension compression members.
Yeah.
Okay, and the difference between a frame and a machine.
Generally, frames are rigid structures designed primarily to support loads, and they're usually stationary. Think building frames, bridge structures. Machines, on the other hand, have moving parts. They're designed to transmit and alter forces. Think pliers, engines, backhoes, linkages.
Okay, so how on earth do you analyze these if you have multi-force members? It sounds way harder.
The absolute key step is disassembly. You have to mentally take the frame or machine apart, draw a separate free body diagram for each individual part,
Every single component.
every component that isn't a simple two-force member. This is crucial because it exposes all the forces acting between the parts at the pins, contact points, etc.
And you still look for two-force members within the frame or machine.
Oh yes, definitely.
Mm.
Identifying any two-force members simplifies things immensely. If you spot a simple link connecting 2 points with no load in between, the force in it just acts along the line connecting those points, makes its FBD trivial.
Okay, so disassemble, draw FBDs for each part, identify two force members. What about the forces where parts connect?
That's where Newton's third law is critical. Action-reaction pairs.
Ugh.
If member A pushes on member B at a pin with a certain force, say 100 N to the right, then member B must push back on member A at that same pin with an equal and opposite force, 100 N to the left.
Equal and opposite.
Always. These interaction forces are internal if you look at the whole machine, but they become external forces on the individual FBDs of the disassembled parts. You must show them, and show them as equal and opposite pairs on the diagrams of the two parts that connect.
That makes sense. It sounds much more involved needing separate diagrams for everything.
It is more involved, but it's systematic.
Hmm.
And identifying those two force members really pays off. There are examples like analyzing a backhoe. Recognizing certain hydraulic arms or links as two-force members drastically cuts down the number of unknowns you have to solve for, compared to treating everything as a general multi-force member.
Yeah, I can see that. A backhoe has lots of interconnected parts. Pliers, too. Simple machines. If you took them apart mentally, you'd see those interacting forces at the pin.
Exactly. The pin connecting the two handles and jaws. Analyzing the forces there explains how pliers multiply your grip force. It all comes down to disassembling and applying equilibrium to each piece.
Wow. Okay, what a journey. We went from just looking up at a bridge to really unpacking the engineering secrets inside.
We really covered the fundamentals, started with trusses, those rigid triangular structures.
Right. Made of two force members, assuming pin joins and loads at the joins.
Then the two main methods. Method of joints, going point by point, using TF-Wavy pounds. Great for finding all forces.
And the method of sections, the strategic cut. Using fix, Cephi, and nem pounds on a segment to find specific forces efficiently. Super useful.
Don't forget the zero force members, the unsung heroes providing stability and redundancy. Remember how to spot them.
Yep, the two rules for inspection saves a lot of work. And then we jump to 3D space trusses, same ideas, just more equations.
And finally, frames and machines. The key there, disassemble, draw FBDs for each part, watch for those crucial action-reaction pairs, and definitely still identify any two-force members to make life easier.
So bringing it back to the listener, why should you care about all this static stuff?
Well, because now when you do look at that bridge or a crane or even simple tools like pliers or maybe a ladder, you have a new appreciation, right? You can start to see the invisible forces.
Yeah, you can kind of visualize the tension, the compression, how the load is getting transferred from one part to another. You can see the cleverness in the design.
Exactly. It's like having X-ray vision for engineering. You understand why it's shaped the way it is, how it manages to stand up or do its job. It demystifies the built world around you.
It really is amazing how these basic ideas of balanced static equilibrium are the absolute foundation for everything from huge stadiums to tiny mechanisms. So here's a final thought to chew on.
Yeah.
We've seen how trusses and frames hide these elegant solutions. What other everyday objects are just waiting for you to unpack their structural secrets? Think about a bicycle frame maybe, or your desk chair, even something simple.
Yeah.
How does it handle the loads? The world's full of these little structural puzzles.